In today's class, we're going to look at concavity, and after that, we're going to look at the second derivative test. But before I move on to our new topics of concavity and the second derivative test, let's talk a little bit about what we learned last class. Well, we learned that the first derivative describes the direction of opening of a function. Right, so we learned last class that the first derivative describes the direction of opening of a function. And so that is, the direction is the intervals in which the function is increasing and the intervals in which the function is decreasing. And remember, we know a function is increasing if the first derivative is greater than 0. We know a function is decreasing if our first derivative is less than 0. And it's constant, of course, if the first derivative is equal to 0. Well, today we're going to talk about concavity. And we use the second derivative will describe the concavity of a function. So if the second derivative talks about concavity, concavity means the curvature of the graph. So if a graph that's curved like this, like a smiley face, that's considered concave up. And if the curve is like a frown, that is considered concave down. To figure out concavity, we look at our second derivative. So if the second derivative is greater than 0, then our function is concave up for that interval. Oops, spelled wrong. But if our second derivative is negative, then the function for the entire interval in which the second derivative is negative, that function or that part of the function would be concave down. Again, I want to do an A there when it should be an O. Try that again. Concave down. Okay. So that's the idea that we're going to look at, is describing that curvature, the bend in the graph, what it looks like. And when I have a graph, for example, let's say I have a graph that starts concave up and then switches to concave down. Okay. This point here, where the graph switches from concave up to concave down, has a special name. This point where the concavity switches is called the point of inflection. So the point of inflection are the points in which the concavity changes from either concave up to concave down or concave down to concave up. Those are our points of inflection. Points of inflection occur when our second derivative equals 0. That gives us our points of inflection. Well, possible points of inflection. We still have to make sure that it switches from concavity from one side to the other. Sometimes you might have the second derivative equals 0, but you could have a point, you can have a concave up followed by a concave up again. That's very unlikely to occur, but that's what we're going to be looking for in order to figure out these possible points, these points of inflection. All right, so let's try one. So let's say if I'm given f of x is equal to 1/3 x cubed minus x. And let's find the intervals in which this function is concave up and the intervals in which the function is concave down is what we'll be looking for. So the first thing we want to do is we need to figure out the second derivative. So in order to get to the second derivative, I have to first calculate the first derivative. So 1/3 x cubed, differentiating that using our power rule, we get 1/3 times 3, which is just 1, x squared minus 1. So this would be equal to our first derivative. But concavity is measured by our second derivative. So I need to differentiate this one more time. So the derivative of x squared is 2x, and the derivative of -1 is 0. So our second derivative is -2. So to find those possible points of inflection, I'm going to take that second derivative and set it equal to 0. Solving this, I get x equals 0. So that's going to be a possible points of inflection. So while I'm going to take a number line, and on this number line I'm going to put in where my second derivative is equal to 0, and we're dealing with our second derivative here. And so now I'm going to do test points on each side of this flag, because this is going to be my key value I'm looking at. So at x equals 0, this is my flag. Okay. And so I'm going to pick a number less than 0 and see what happens. So in my test value here, if I plug in, say, -1, well, 2 times -1 is going to give me a negative. So that's less than 0. So if I'm negative, that means I am concave down over here. Then I'm going to try something greater than 0. So let's try 1. Well, 2 times 1 gives me a positive value. And positive second derivative, we learned on the last slide, means it's concave up. So these are my intervals. So my function is concave down, concave up from this point of inflection. So now we know it does switch from concave down to concave up, so this is a point of inflection. And so my concave up interval is from 0 to infinity, and my graph is concave down from -infinity to 0. So that's looking at my concavity. I just realized I forgot to say something because it doesn't apply in this situation, but where points of inflection occur where our second derivative equals 0, or when our second derivative does not exist. But again, our second derivative was a polynomial, so it always exists. So I didn't have that rule here, but you need to realize that that still applies. So we're finding we're using the same process as finding the critical values with our first derivative. We're doing the same process with the second derivative to find these possible points of inflection. So graphically, not dealing with this problem here, but for any points of inflection, we can have a couple of situations that concur. I just kind of want to look at this kind of graphically. So I could have, let's say I have a concave up, and then it switches to concave down. So I got concave up to concave down. So this is our point of inflection. And if you'll notice, this is concave up, and so every one of my tangent lines will be below the graph, or the graph is above all the tangent lines. And when I'm concave down, the graph is below all of our tangent lines at any given point on that curve. But at that point of inflection, our tangent line will be vertical like this. So we can have this situation going on. We have our tangent line is vertical. Or we could have, let's say, concave down, and then our point of inflection, and our graph switches to concave up. So we can have a graph that looks like this. So concave down, our function is below all our tangent lines. Concave up, our function is above our tangent lines. But at those points when we switch from concave down to concave up, our tangent line will be horizontal, and that will be equal to 0. So that's our slope of our tangent line. Here is equal to 0. Okay. And here, our slope of our tangent line is undefined. Does not exist. So that can give you some, those are the basic two that I'll look at. Those are the most common two that you'll see on how those points of inflection, because that's when you switch from one concavity to the other. So you're going to look basically at those two shapes. Okay, let's put this information together in an example problem. So we're going to do some things that we learned last class and some of the new things we just learned today about concavity. So looking at our function f of x is equal to, so our f of x is equal to x to the fourth minus 4x cubed. All right, first thing I want to do is I want to find the critical numbers. So remember, that is when the first derivative is equal to 0 or first derivative is undefined. So find the first derivative. Well, using the power rule, x to the fourth derivative is 4x cubed. And negative 4x cubed, well, that would be equal to negative 12x squared. So that's going to be my first derivative. It's a polynomial, so it's differentiable everywhere. So all I have to do is take that first derivative and set it equal to 0 to figure out what that occurs. Well, I notice I have a 4x squared in common, so I factor that out. That leaves me with an x, and this leaves me with 3. And so 4x squared equals 0 when x equals 0. And x minus 3 is equal to 0 when x equals 3. So our critical numbers would be x equals 0 and x equals 3. So those would be our critical numbers for this problem. We want to find the intervals for which this function is increasing or decreasing. To do this, I need to look at my sign chart. So I'm going to construct a sign diagram, sign chart here, and put my critical values on here in increasing order. So I got 0 and I have 3. And I'm going to make a table of values. And I'm looking at my x values. And I'm looking at increasing or decreasing. So this is where I'm focusing on the derivative. So our derivative is 4x squared times x minus 3. And I want to figure out when this is positive or negative. And so since my key values are at 0 and 3, let's make that 3 a little bit clearer to see. 0 and 3. I'm going to choose points in each of these intervals. Notice I've divided the number line into 3 sections. And so my first intervals are numbers less than 0. So let's try negative 1. Plug in negative 1 here. Negative 1 squared is 1. 1 times 4 is a positive. And negative 1 times minus 3 is still negative. And anytime I take a positive times a negative, that's going to give me a negative. So I know that is negative. Then I'll try something in between. So let's try a positive 1 this time. So this first term, 4 times 1 squared is going to be a positive value. And 1 times a negative 3 is going to give me a negative value, 1 minus 3. And so positive times a negative is a negative. So this is still negative. And then I'm going to try something greater than 3. Let's look at 4. 4 squared is 16. 16 times 4 is definitely a positive number. 4 minus 3 is a positive number. Positive times a positive is equal to positive. Okay. So this tells me that this is my derivative. And if I wanted to talk about my function, if I wanted to talk about this function here, if my derivative is negative, that means my function is decreasing. So that's be decreasing. If my function is negative, my function is still decreasing. And if my derivative is positive, my function is now increasing. So for what intervals for which is our f increasing? Well, f is increasing from 3 to infinity. So that would be our intervals in which it's increasing. The intervals in which it's decreasing is negative infinity to 0. But at 0, technically it's neither increasing nor decreasing because our slope of our tangent line is 0 there. So we would break this up to say from negative infinity to 0, union 0 to 3. And that's when it would be decreasing. So we do break that up to those two pieces, but all of that is decreasing except for the value of 0, in which it's neither decreasing nor increasing. It's constant at that value for that instant. All right, we're going to use the first derivative test to find x values in which we have a maximum or minimum. Well, we were decreasing, then decreasing again, and then we switch from decreasing to increasing. So here's the only one that we have would be a maximum min, and that gives us our minimum value at, oh, we just want x values. So let me fix that, just the x values. So that'd be a minimum at x equals 3. Okay, so now we're going to look at finding the points of inflection or intervals in which the function is increasing concave up and concave down. Both of those things are found by looking at our second derivative. So we're going to go up here to our first derivative. F of x is equal to 4x cubed minus 12x squared. And we're going to find our second derivative. So we're going to differentiate our first derivative. So 4 times 3 is 12. Decrease my power by 1 gives me a 12x squared. Using the power rule here, that gives me 24x. So we have 12x squared minus 24x would be our second derivative. Since this is a polynomial, I know it's differentiable everywhere, and so the derivative always exists. So I don't have a derivative equal to does not exist. So all I have to do is figure out when this derivative is equal to 0. So taking out my GCF of 12x, that leaves me with an x minus 2. And so setting the 12x equal to 0, I get x is equal to 0. And setting x minus 2 equal to 0, I end up that x equals 2. So I'm going to do a new number line. And this number line is dealing with the second derivative. And my key values for my second derivative is at 0 and 2. So I'm going to flag those values on my number line as important values. And I'm going to make another table. And this one is dealing with my second derivative, which is 12x times x minus 2. And I'm going to notice I again divided up the number line to three parts. So the first part is negative infinity to 0. So I'm going to choose a number in that interval. I'll choose negative 1. Plug it into the second derivative. I get a negative for this first term. And I'm going to times that by, well, -1 minus 2 is still negative. So negative times a negative gives me a positive. So my second derivative is positive for this interval. And I'm going to pick a number between 0 and 2. So let's choose 1. Plugging that in, 12 times 1 gives me a positive value. 1 minus 2 gives me a negative value. Positive times a negative is negative. So this is second derivative is negative there. My last piece of the number line is this area from 2 up. And so I'm going to pick a number greater than 2. Let's try 3. 12 times 3 gives me a positive number. 3 minus 2 is also positive. Positive times a positive is positive. Okay, so this is what's happening on my second derivative. So if my second derivative is doing this, my function value will be doing the following. If my second derivative is positive for my function value, that means that function on that interval is concave up. My second derivative is negative. That means my original graph must be concave down for that interval. And if my second derivative is positive, the original function is concave up. So notice that at 0, I switch from concave up to concave down. So that's a point of inflection. And at 2, I switch from concave down to concave up. So that's going to be a point of inflection. So since it asked me to find the points of inflection, I'll need to write this as an ordered pair. I know my x values will be 0 and 2. So to find my y values, I go back to my original function and plug in each of these points of inflection. So 0 to the 4th minus 4 times 0 cubed is 0. So I have 1 point of inflection at the point 0, 0. All right, now I'm going to plug in the other point of inflection, which is 2. So 2 to the 4th minus 4 times 2 cubed. 8 times 2 is 24. 16 minus that will give us negative 16. So my points of inflection will be the order pair at 0, 0 and 2, negative 16. So those would be my points of inflection. Now to find my intervals in which the function is concave up and concave down, I just go back to this new sign chart for the second derivative. And I know it's concave up on this piece of this sign chart. So I know my function is concave up from negative infinity all the way up to 0. But it's also concave up in this interval here. So also from 2 to infinity. And we'll be concave down in this piece here on our sign chart. So that tells us we're concave down from 0 to 2. Alright, so that's how you do how you figure out your points of inflection and your concavity up and down. So we'll pause this video. Right, now we're going to look at finding the second finding your maximum and minimums using a process called the second derivative test. Now the second derivative test does the same thing, well, it allows you to find the same results as your first derivative test. It helps us identify the extremas of a function. But the second derivative test is much more faster and requires less work. You don't have to make a sign chart. But unfortunately, although it's quicker to do, it does not work in all situations. So in some cases, the second derivative test will fail. If it fails, you have to fall back and do the first derivative test. All right, so the second derivative test, basically what you do is you need to first find your first derivative because you must identify all critical points or critical values, x values in which the critical points occur. So your critical numbers you must first identify. So you find your first derivative. Set your first derivative equal to 0 or where it does not exist to find all your critical numbers. Then, instead of making a sign chart, all you do is find your second derivative and then plug in each critical number into your second derivative. So we're taking our second derivative and we're going to plug in each critical number. So each C value, which is a critical number. And here's the results that you get. If the second derivative of that critical number is negative, you have a relative maximum or local maximum. If that second derivative, if you evaluate the second derivative at the critical value and you get a positive result, you have a relative minimum. If you plug it into your second derivative, the critical number into your second derivative, and you get 0, you could have a relative max, you could have a relative min, or you could have neither. This is the case where the test fails. So this is the case. If you get a 0 in your second derivative when you're substituting in your critical number, then this second derivative test fails and you have to go back to the first derivative test. So that's the procedure that we're going to do. So let's do an example. Okay, so let's look at an example. Let's say h of x is defined by 3x to the 5th minus 5x cubed plus 3. And we want to figure out the second derivative. We want to find all our extrema values using our second derivative test. Okay, so first thing I'm going to do is step 1 is to find your first derivative. So that gives us 15x to the 4th minus 15x squared. And then derivative of 3 is 0. And so it's a polynomial, so it's never undefined. So I just need a set to find my critical numbers. I now want to set my first derivative equal to 0. I can factor out a GCF of 15x squared. That leaves me with an x squared minus 1. So that becomes 15x squared, and this is x minus 1 and x plus 1. So I have my critical numbers will be x equals 0, and then when this x minus 1 equals 0 when x equals 1, and x plus 1 equals 0 when x equals negative 1. So those are my critical numbers. Now that I found that, instead of doing a sign chart, what I can do is I can now find my second derivative. So my first derivative is 15x to the 4th minus 15x squared. My second derivative will be 60x cubed minus 30x. And then I'm going to evaluate this second derivative at our 3 critical values here. So let's say I'll do it in increasing order. So let's do negative 1. So 60 times a negative 1 squared minus 30 times a negative 1. Well, that gives me 60 plus 30. Oh, cubed. Whoops, my bad. Can't read. I messed up in my own writing. That's a cube. Alright, so cube there. Alright, so that gives us a negative 60 plus 30, which is negative 30. And negative 30 is less than 0. So since my second derivative at x equals 1 is less than 0, I have a local maximum at x equals negative 1. Okay, now let's try at our second derivative at 0. So that's going to be 60 times 0 cubed minus 30 times 0. Well, that's just 0. Uh-oh. that was a case that the second derivative test fails. All right, and I'll come back to what we have to do in that case when the second derivative test fails. So now let's look at our third critical value point and see if it works. So our second derivative at 1. Well, that's going to give me 60 minus 30, which is positive 30, which is greater than 0. And if my second derivative at my critical value is positive, that means I have a local minimum at x equals 1. So I figured out 2 of my extreme values. And notice it didn't take me too long to do that. But I have a problem with this one here at 0. So the second derivative test did not work for this critical value. So that means I must now go back and do the first derivative test. So now I must change over and do this to the first derivative test. So we got to do our first derivative test now. And we only need to do it on the piece that did not work, the 0. So I've already figured out my critical values. And so my critical values I know to be -1, 0, and 1, which is written right here. So those were my flag values. Those were my critical values. And I've already figured out that this one right here is a maximum, and I figured out that this is a minimum. So all I care about is this value. So I need to know what's happening in this interval and this interval. So it's a little mini second derivative test. So I'm going to look at a number in between 0 and -1, so -0.5. And I'm going to look at a number between 0 and 1, so we're going to do 0.5. And we're going to plug that into our first derivative. So our first derivative was in factored form 15x squared times x minus 1 times x plus 1. Okay, so that was our factor form of our first derivative. You can see that here is our first derivative. There's our factor form right there. So that's where I'm getting that from. Okay, and so again, I only care if it's positive or negative, so I don't really care about the sign. So if I plug in a -1/2 here, squaring that times by 15, that's going to give me a positive. -1/2 squared is -1/4 minus this, so that's going to be a negative. -1/4 plus 1 is going to give me a positive. So I got a positive times a negative times a positive, which equals a negative. So this is going to be negative. And then if I plug in 1/2, that gives me a positive. 1/4 minus 1 is negative. And then 1/4 plus 1 is positive. And so I end up with a negative. Now, since I went from negative, I'm decreasing, and I'm continuing to decrease. That means there is no max or min here. So this is one of the examples where it did not have a max and min at that critical value. And so that is how you do the second derivative test that's how we do the second derivative test. So it's a shorter way of assuming if it works on those critical values. It's a shorter way of finding your local max and mins. Okay, so now we have learned all the information for this section. So you can go ahead and finish the Canvas quiz that is titled Concavity and the second derivative test.